You know what the Lebesgue number is? Is it in that book? Probably is. Is that Alec Prentice and Market Shaw?
Yep.
Oh, it's in that book. Yeah, I thought you had your. Was that other book? Yeah. No. This is the analysis book from last time. What's a Lebesgue number? Well, who or what has a Lebesgue number? A covering has a Lebesgue number. Here's the deal. This is what it tries to capture. Suppose I have a set of numbers here between A and B, and I cover the set A and B. So how am I going to do this? That's an interval. This is an interval. This is an interval. And this is an interval. You see how I've parenthesized this? So the closed interval AB is contained in these 4 open sets. Okay, that's a covering. A Lebesgue number is a delta such that if you are if you are a little open set, no more than delta y, you will, no matter where you're centered along here, you will be inside one of the given covering sets. All right. Well, how could it happen that you weren't inside? What if you were this particular one? I'll do it down here so I'm drawing this plugger. What if you were that open set? You're not inside just one of them. You're overlapping 2 of them, right? You're overlapping this one and this one. You've got 1 foot in each camp, right? But if you were really, really small, wouldn't matter where you were. You know, if I had parentheses like this, do you see that I could put that pair of parentheses anywhere along here, and at most it would just be within one of those things? It could be within 2, but it's going to be wholly within 1. It will not be split. You see the difference between this and this? This one has a foot and 2 camps. No matter where you put this one, he's always totally within 1. Is that obvious? You know, where you can put him, well, if he's here, you're in good shape, but you can even put him like here. There he would be wholly in this one and wholly in that one. Right? Okay. Something happened as I went from this width to this width. I passed the Lebesgue number of this covering. I got smaller than the Lebesgue number for the covering. Once you pass it and get smaller, this property ensues. You are then wholly within one of these things, okay? All right. Now, it might be nice if you start, well, it's a separate issue to prove that every open cover of a closed and bounded set has a Lebesgue number. So every open cover of a compact set has a Lebesgue number. Would somebody like to prove that next? That proves something. Who would like to prove that? You want to prove it? You got a lot to do. Okay. That's probably probably there. Prove that every open cover of a compact set has a Lebesgue. Okay. And then after we have that, you would like to start with the assumption that we always have a Lebesgue number and prove Hein's theorem using Lebesgue number. Try to say that fast after you have 3 or 4 passes. Okay, you're going to prove that a cover has a Lebesgue number, and after you assume that a cover has a Lebesgue number, you get Hein's theorem out of it. Now, I don't think you have to go too far. What?
Please state clearly issues like the covering sets.
AB is a closed interval. The covering sets are open sets.
And they do overlap.
And the union of the open sets covers AB. There's no cardinality. Of course, you know, since AB is closed and bounded by Heisenberg, there's a finite. And that will come into the existence of the Lebesgue number.
Okay.
Then once you have a Lebesgue number, proving continuous functions are uniformly continuous, well, you think all you have to do is use the delta that comes from the Lebesgue number and use that for your delta to keep x and y close together, then you can control the variation of the function. Try that if you have to. You might have to adjust that. Okay? All right, great. Right on track. Now, let's approach the whole business of the Cauchy integral. I have a sum. Excuse me, k equals 1 to n, and I want the limit as the partition norm goes to 0 of this thing, and this will be x sub k minus 1 delta x sub k. Okay, great, that's a Cauchy sum. All right. Well, I'll tell you what, let's have a two-pronged approach here. First of all, let's get a candidate limit. Somehow, by hook or by crook, we'll get a candidate limit for this. And then the second phase of our efforts will be to show that it doesn't make a damn bit of difference what the partitions are as long as they get small. Okay? You guys did this already?
Well, the partitions go to 0.
Did it small?
They get smaller, smaller. We did that.
Okay, but where's the limit come from?
That I don't remember. I think it was just given.
Ah, okay. It's often given in the definition. We're going to bootstrap it here. All right. So let's take the interval AB and divide it into just divide it in half. So the first partition consists of A, which is x0, and then the intermediate point x1, which is going to be a plus b over 2, right? And x2, which is going to be b. So that partition is determined exactly. However, I might add, there is a Cauchy sum, take that out. There's a Cauchy sum using this partition, right? All right. So we'll call that P1. What's the norm of P1? It's B minus A over 2. Okay. Partition P2. No, A. Sorry.
Oh, I'm sorry.
You are so critical of my penmanship. There. How's that? You can't see it. My thought is internal. All right. I want to go to the quarter points now. I want to cut everything in half. So x1 is going to be what? A plus b over 4, right? x2 is that the old x1, right? x3 is 3a plus b over 4, and x4 is b. What's the norm of P2?
B minus A over 4.
Is there any doubt in your mind that I can continue doing this by bisecting each subinterval? And then the norm of the nth one of these things will be b minus a over 2n. Okay, so the limit as n goes to infinity of the norm of the partition is going to be what? 0, right? We're getting there. All right. For every one of these partitions, there is a Cauchy sum. You know, I go back and I just plunk it into this part, not taking the limit yet. I create that sum. I go find what that sum is for every one of these partitions. Okay? I can do that. All right, and now I claim that those sums let's suppose that the sum after the, for the nth partition, the sum n is this. One, two, oops. No, this isn't good. Let's call this T, S and T. Is the sum from 1 to n f of x and k minus 1 to x, k. Partition used is the teeth partition, okay? So after the teeth partition, I have the Cauchy sum as S and T.